So without further delay, let me introduce the first speaker of this session. That will be Anton Elita. Anton Elita is a technical solution architect at Juniper Networks. His area of interest are routing and automation, and his previous experience has included work at Tier 1 ISPs as a network engineer, architect, and solution consultant. So please join me in welcoming Anita to the stage. Thank you. Anton, sorry. Let's start that again. You see, this is what happens when I don't drink coffee. Okay, so forget that last bit. So please join me in welcoming Anton to the stage.
Thank you. I paused for a second to not to occupy somebody else's place, but yeah. So my name is Anton Elita. I'm part of Juniper Networks, and I'm doing technical solution architect work, and I'm involved a lot into routing and automation tasks in my daily life at work. And today I thought we could touch a little bit on segment routing, on core networks of service providers, enterprises. So let us see if there are any interesting topics for this matter. So I put a question mark here just to give you a sign that we always need to question if a new protocol, new technology is bringing any innovation and what are the applications for this. This is kind of overview of what segment routing is addressing. So no matter what type of the forwarding plane, but segment routing was perceived as a protocol which is working independently in a distributed fashion. It is aimed to help service providers and enterprises run their networks with multiple customers. So first application you would probably think of is separating VPNs, providing L2 or 3 VPN services of different kinds. But as well, there is a plethora of applications that segment routing is addressing. Over the last years that segment routing has been there, we have seen different trends in developing segment routing. Well, one is trying to catch up with existing protocols. So you know that before segment routing there was RSVP, there was LDP. So this is one direction, and in some points still catching up, right? And other things is actually where the innovation of segment routing is happening. So in my view, from what our customers are using and what we are developing is actually around Flex Algo, TI, LFA, microloop avoidance. Of course, you could add a couple of other things that segment routing brought in, but in my perspective, these are the main areas that differentiated from previously developed MPLS-based protocols. So segment routing can operate as independently, like on box routing decisions, distributed, and this is actually the reason why we still have internet, right? So internet started as a distributed network, and we still want to keep it probably in this fashion. But to give more value to your customers and to your network itself, there is place to do some control based solution like central controller over segment routing, not necessarily the full routing taken over a controller, but maybe a combination like a hybrid solutions. Controller definitely can add some value onto it. And when we talk about segment routing, we usually think of as well forwarding plane, because it started with SR MPLS-based forwarding. Many people might not know, but it's not necessarily to run IPv4 control plane when using SR MPLS. But this is kind of a trend or demand in the market to run SR MPLS with IPv6 control plane. So actually you don't use your LinkNet IP addresses in form of IPv4. You use it as IPv6, your loopback is IPv6, your management IPv6, your protocols, T1, whatever you use, BGP, everything is v6, but you use forwarding plane based on MPLS forwarding. And we heard today as well that like in data center networks, it's really important to understand the hardware capabilities for the switches that cannot run MPLS in certain cases. Similarly, in service provider networks, the equipment as well can be limited to certain forwarding planes. So if your hardware is supporting MPLS and you would want to run IPv6 control plane, it's perfectly fine. One other data plane that is emerging really, really fast, and you hear about it probably very often, is SRv6. And SRv6, although it's very young, it exists already in two kind of flavors on the forwarding plane, compatible with each other. And it is SRv6 with compressed SID and SRv6 with the so-called classic SID. So the bubble with the SRv6 with classic SID is kind of red because, well, for traffic engineering purposes, it's not effective to stack so many IPv6 addresses. They're very long, and this work is having less traction in recent years, months, and the industry converges towards so-called compressed SID, where you put all your forwarding instructions, maybe your VPN encoded next hops right into the IPv6 address. Well, let me try to review the breakthrough innovations that segment routing brought with it and that we didn't have before. So we probably heard about loop-free alternate. Loop-free alternate is programming next hop before the failure happens, right? So when the link or node goes down, you have an alternative path, and you can switch in under 50 milliseconds. Usually this is the requirement to another path. So this must happen in hardware, this switch over, so there is no time for the control plane to take this decision. So TI-LFA is actually extending the older LFAs like LFA or RLFA, remote LFA, to great deals. So because you can now stack the labels, so you cannot achieve the same with one single label. You need to stack a couple of labels to achieve any kind of topology coverage. And this is an example where you have, say, a link which is failing, and you have some metering maybe that is acting as a backup for the failed link. And there is a prohibitive metric between P3 and P4, right? So that you can cover both the so-called P and Q spaces. We'll not go into the details. With a stack of labels, and you need just two labels on top, the blue labels, to overcome this, a prohibitive metric and forward the traffic in a very fast way over an alternative link. And this path which is calculated is actually calculated by the shortest path first, by your favorite IGP, ISIS, or OSPF. So actually when the link, or when the convergence, better say, is restored or completely in sync on every node, you don't need to switch to a different path because of a different metric, as it's already done beforehand. While TI-LFA is definitely applicable in segment routing networks, we need to understand that there are two types of segment routing forwarding. So one is simple, based on the destination label with a single label, but as well we have SRTE, so traffic engineering, where you put kind of few labels in the stack when you want to achieve a certain path through a network. And when we talk about node protection, there is one thing that you need to know, is that with SRTE, it's not always possible to do node protection. So if you do implement this new technology, you need to keep that in mind. Just imagine that you have these two paths, the green and the blue path. The green path is able to do node protection and the blue cannot, just because the green path has a destination label of a remote node, not the one which is failing, so we can protect this label. And if we pick up the blue path, then our next hop is actually the failing node. So the outer label will be actually the label of the failing node, so we cannot protect this label as it is actually failing. So in order to protect it, you will need to look up next label in the label stack. So whenever you enable TI-LFA for node protection, you would need to keep that in mind. One other important innovation that is of interest to many customers is to bring segment routing support into BGP, and this happened already a couple of years ago. So we can distribute sRGB, so global place, in BGP messages, which is optional, but as well we can distribute the prefix SID in the BGP update. Imagine a network relying on BGP LU, so labeled unicast. On the left-hand side, you will see the labels allocated by PE1, sending them to ASBRs, SBRs doing next hop self. But every SBR has a different decision what label to program and to send by control plane to the remote device. So one SBR picks up label, say 20, another SBR picks label 30. So they're not in sync. So in case when a node fails, we need to wait for BGP convergence to happen before we can restore the traffic. And this usually takes more time compared to IGP convergence. So what problem do we solve here? Is actually we do anycast seed or anycast IP address used by those two ASBRs. So they advertise the remote prefix of PE1, putting next hop self to this anycast IP and label. So what happens when the link or node is failing, like ASBR1 or ASBR2? The other node is already pre-programmed to take the traffic incoming to it with the same label and forward it, teach it to a different label on the other side. This has been tested as well in different interop scenarios. We had one of the previous speakers, Johan, was talking about ENTC, and this is a very important event to do the interoperability testing between vendors, and such scenarios as well part of such testing. One thing which is easy, or not so easy actually, very hard to catch, but easy to avoid, is microloop. So when some nodes in your network, like in this example R5 and R4, are a bit slower from the control plane, or maybe very, very busy during the time of some remote or local failure, like R2 or R3 link is failing, then those two nodes might actually send traffic back, so loop them back towards the originator, just because they didn't realize there was a failure in the network. So how can we protect here? So we actually, once we have learned about local or remote failure, like the R0 in this example, it learned about remote failure, and it knows that there might be some slower thinking nodes in the network. It would program, at the time of failure, would program the path, the new path, with a label stack, so that the R5 and R4 will never have a possibility to loop the traffic back, just because the label stack advises those two devices to forward the traffic over certain links and not according to their SPF calculation, which is whatever in their routing information base in the RIB. Microloop avoidance is possible both for local failures, remote failures. It is really important for events like link up, link down, and as well metric change. Microloop avoidance as well can provide you with ECMP. Like in this case, we have two paths from P1 towards PE2, so two different paths, so that the protecting router PE1 is able to create, for example, two ECMP paths to split the traffic during microloop avoidance. Good thing as well, microloop avoidance as well as TI-LFA discussed earlier works within the flex algo, within the topology. Many would as well think, do I need segment routing traffic engineering, or should I be happy with flex algo? So flex algo is very lightweight traffic engineering, where you create additional topologies, something that service providers have been asking for decades, but there was no great solution. Well, flex algo tries to address this demand and creates a topology per certain constraints. So your topology can look like just use the paths with lowest delay, or maybe your topology would include only paths without delay variation, not higher than X, or maybe only paths of bandwidth not less than, say, 10 gigabit, whatever. So when you created this topology, or the definition, better say, every router has to participate in this definition, the routers that need to participate. So this information is disseminated to every device. So even P devices, they need to have this knowledge. and it works completely on shortest path first based, which is good and bad at the same time. It is good because you can do the ECMP, so equal cost multipath. You can split the traffic evenly. But it is bad because it reduces the scale, right? So if you have multiple topologies, you do the SPF runs in every topology on every link, up-down metric change. So imagine that in a larger network that might not scale that as good as if you had only a single topology. Compare these to segment routing traffic engineering, you can solve similar tasks and you need to program only the ingress devices. Like in this very small network, you have 2 ingress devices, 2 PE routers, and you can program them the way that you want, or they can program themselves actually. So you could do the computation like you do with RSVP. You give the constraints, and the constraint is per programmed tunnel, is not per topology or whatever like in FlexAlgo. So it is you can provide many more combinations of this. You could extend the traffic engineering database by introducing BGP data from a remote autonomous system. Like even if you don't have IGP connectivity to the remote domain, you send the BGP link state information over the fence, over the IS border, and you use this information to create end-to-end path across multiple autonomous systems. This is what segment routing traffic engineering is offering. And actually, you can do even more than this. You could use so-called on-demand next hops. So this is as well another big problem for service providers. How do I create a full mesh of my end-to-end LSPs? So I have so and so many PE devices. I add and remove PE devices daily basis, and I forget to create LSPs from A to B. So for this, we have the on-demand next hops, which is actually acting in like a 3-stage manner. First, you send a prefix from some remote PE. Hey, I have this VPN now. So I just configured this VPN. I have an interface came up in this VPN. And now I'm PE1. I receive this update. I look into my tables. And I see, well, I don't have the next hop to this remote PE. So how do I send traffic to him? So this is where you can automatically, so completely fully distributed on the ingress PE, on PE1, create the traffic engineering tunnel. So it happens completely automatically. It's brought up according to your constraints. So you define a template. Template is saying that I want to use red links only. And then you create a SRT according to this template. Or you can offload the computation to a controller if you rely on a controller to do the computation instead of locally decisioned LSPs. When we talk about controller, I really think that there is an application for this. Even without giving full control of a network to a controller, you could do things like congestion avoidance, where you collect data from your network. One link goes red, it doesn't have enough bandwidth. You do make before break alternative LSP. You move the traffic to this new LSP, and you don't have congestion anymore. But for this, you need to have a global view. So this is something really hard to solve in a distributed fashion. So this is one application scenario where you would need a controller to do this job. And maybe addressing a little bit question where you would need different forwarding planes. So one example where you would need different forwarding planes, or actually interconnecting large networks, would be first, I would start what service providers used until now. Is actually BGP labeled unicast, where you have multiple domains, a national core, international core or multiple cores, aggregation areas with tons of devices, and run networks with many devices. So thousands of PE devices. To interconnect them on IGP level is really difficult. So IGP scale to a certain extent because of the SPF runs, because of the faster convergence. So they are limited in actually the flooding domain. BGP solves this problem nicely. So you could really scale up to millions of devices and hosts. But BGP-LU has one say, not a drawback, but actually, actually a drawback, that you don't have a possibility to decide on service type that it is, carrying. Like if you want a service to be different from another service, you don't have a coloring here. So BGPLU has one single next hop. You create this next hop, and all of the traffic, your low delay, your mobile backhaul traffic, and as well your cat videos, all go via the same path. So color is missing here. To address this, there are a couple of initiatives, sometimes competing initiatives, and they do it with introducing color to BGP. So now BGP is able to not only give you the next hop, but as well say this next hop has this color, and color actually means your intent. If your intent is low delay, then you pick a color 33 for this, and this is your code for the low delay routing, and you transport this color alongside with the IP address when you, and label, of course, when you use BGP LU-like protocol. So in this case, it's an example of BGP-CT, and you could use different forwarding planes with this, so you could use MPLS or SRv6. And one other example of interconnecting very large networks, when you want to get rid of BGP completely, then you must use SRv6 for one simple reason. SRv6 provides you a possibility to summarize. So you create actually a subnet corresponding to all of the IP addresses in this region. And this, well, two or maybe subnets or three subnets, but a few subnets, so to say. And you advertise this subnet across the area border. So in this case, you don't need any BGP, so you can use your IGP, ISIS, multi-instance ISIS, or multi-instance OSPF, if you want to go this way for SRv6. And to do coloring, you would probably resort to Flex Algo, to the lightweight traffic engineering, because heavyweight or fine-grade traffic engineering is as well still a complication here. And this is where we have, the SRv6 as a good example for such a solution in very, very, very large networks. And now it's not yet time for the beer. I mean, it's time for the beer, but not that other beer, which is in the evening. So let's talk a little bit about multicast. So Johan as well spoke about multicast in data center, and I wanted to address a similar, design approach in service providers, so large enterprises. How do you solve multicast? So today we have PIM, PMv6, MLDP, RSVP, SRP2MP, same for V6, but all of them create state in the network. So segment routing is something which doesn't create state. So you don't want to have this control-based information on every hop. You just want to distribute it via your ISIS, and hence programming the labels according to the information from IGP without having additional protocols and additional state. So we have a very, very nice solution coming from IETF. It's pretty old already today, like 5 years, but it took the industry quite some time to start, just because first it's a new forwarding plane. It's a very nice solution, but a new forwarding plane is required. So this is already kind of a blocker for starting implementing this out there in the wild. And second is that service providers first try to solve the unicast routing, and then they switch their attention to multicast. So with beer, it's very, very elegant solution. You do the replication in the core, and in the core you don't have to carry any per VPN state. So you need to allocate the bit forwarding index, so the so-called bit index. Every router has their own bit in the bit string, and this bit string is actually composed out of many bits in the forwarding hops. Like if you take the P1 here, P1 has received from PE1 a bit string of 01001, and this is an encoding that we have two interested receivers for this bit string. And these two interested receivers are PE2 and PE3. And when it does the replication, so until P1 it's not replicated, it's just one packet, and P1 splits it into different directions because the metric suggests it's the best way to reach the destination. And when it splits or multiplies the packet, it actually changes the bit string. If you look at the blue rectangle, you will see that on the north bound it is 01000, and diagonally it is 00001. So the bit string as well changing. And the labels, so this is an example for a beer with MPLS forwarding plane. The labels are specifically allocated as well for this lookup. So whenever a beer talking router receives this special label that is allocated by itself, it will need to do another lookup in the beer forwarding table. And then it encapsulates new bit string and new MPLS labels. Very nice solution. They're very prospect looking, so this is about the future. But if you're participating in IETF discussions, please join those and see how this can help your organization further on. So today, for multicast options, and I promise this is the last slide, that we have, for the prospect, we have the beer as a protocol or the future for the multicast. But still, is nothing wrong that whenever, if you don't have any other opinion, right? Because according to segment routing principles, there are not many alternatives. You could run your traditional multicast alongside with segment routing. So you run unicast with, without RSVP, LDP, but you run your multicast, if you like, with ingress replication or P2MP. If you want as well, you could as well go for control signal multicast. This is possible as well with Tricit or SRP2MP. So I think I've been running through the slides really fast, but time is time. I don't want to delay other speakers. Any questions, if you have, please ask.
Any questions for Anton? Okay, well, please join me in thanking Anton for a fantastic and very timely presentation. Thank you, Anton.